This is just gonna be an overview video about processing. I know a lot of you will need to take processing classes in the future. So more than anything right now, just to go over some of the basics, touch on some key points, maybe refer back and tie some of the things that we've discussed so far in with the processing. The first thing is, I know a lot of people are mechanical engineers taking the class, and so there's a lot of different types of materials that are out there when we are dealing with engineering. But a lot of the materials that I know that people want to use are things like steel and aluminum. But even there's a lot of different types of steel and aluminum. And they use these codes to help you be able to know exactly what type of aluminum alloy you're using or what type of steel you're using. And I just found Wikipedia pages on these. So here's the one on steel. And as I'm doing this, I said this to past students before, maybe I've said it in some of these videos, but Wikipedia is not a good place to source to say that you got information from, but it's a great place if you're just looking for information, and then you can always go back and find out where that information actually came from, find that primary source. So we can see here that the major classifications of steel, if I click on this footnote here, what it does, it takes us down here to the footnote, and then I can go and I can look at these articles and these sources, and they might be a little bit more accurate. Well, I shouldn't say they'll be a little bit more accurate, but they are actual sources, something that you can source. Don't ever source Wikipedia. Why am I showing you Wikipedia then? Because it's just a good place where a lot of things come together. So you can see that steel has a lot of different things. They have just the basic information about the different types of steel, a little bit more information, maybe some percentages. And as we scroll down, getting into stainless steel. And so there's just a whole lot of these numbers, and this isn't everything. And so when you start doing some engineering, you're going to maybe have to use some steel or some aluminum, and you might not know what type you want to use. This is a good place to kind of figure out what different types there are, or if you're given some type of steel or aluminum, you can look it up and you can figure out what it is made up of. And so here's aluminum. Real quick, I'm not really talking about any of them in particular. I'm just showing you that they exist and kind of what's here. So again, different types, and we get the tables. And so you can go through and you can find a lot of these things. So if we scroll down, different cast alloys, information on them. So there's just a whole lot of information here. And I'm just putting it out there so that you know that it exists if you ever need it. So why are there so many different types of alloys? So we alloy things so that they have different properties. This is going to go back to the introduction video, which I will click on here. Remember that the whole point of kind of this material science, materials engineering, it brings two worlds together. It brings the people who have learned how to engineer. It brings that together with different materials. And so when we know how to engineer, and then we bring the proper materials together, there's products we can make. And if we always follow this line back here, we see that it always comes back to what's the composition and what's the atomic arrangement. And so when we process things, what we really want to do is we want to know what is the material made out of. So what alloy is it? What atoms are in it? But also, what is the atomic arrangement of those atoms? And that's exactly what we're going to be talking about here. There we go. And so what we do is we need to figure out what the composition is. We need to figure out the microstructure. I'm going to go over real quickly just some methods that you can use to change some of these properties. And for the most part, we're dealing with a specific alloy, a specific material, And so these would be ways to change the microstructure. So one of them is called grain size refinement. What that does is it reduces the grain size. In so doing, it increases the grain boundaries. We call that a fine grain material. And what this does, it strengthens and toughens a material. It makes it so the dislocations, it reduces dislocations and makes it so slip can't happen, because if you have smaller grains, those dislocations can't move as much. And one way to do this is to induce nucleation sites. And so when it solidifies, instead of trying to make them nice big grains, we solidify it and we allow it to solidify at many places all at once. I believe there was a picture of it in a past video. So we have this picture here where we have these nucleation sites where crystals begin to grow, and eventually they're going to bump into each other. That's how we get grains. The more places I can get these crystals to begin growing means that they're going to run into each other sooner, and the grains are going to be smaller. So if I can get them to all these things to crystallize a little sooner all at once so that they don't all come together, that is one way to get nice small grains. Another one's called solid solution strengthening. I can add impurities. In other words, I can alloy a material. And what I'm going to do is I'm going to put substitutional atoms in or interstitial defects into it. And what this is going to do is it's going to add defects to the lattice. And these defects are going to change the stresses and the strains between our lattice. I have, let's see, go back maybe to some of these ones. I think this is a good opportunity for us to go back and look at some of these past things that we've discussed. So we have this picture here of a lattice. And when all these are identical, when all the atoms are identical, what's happening is there shouldn't be really any weird stresses or strains within the material. But when we had this, when things didn't quite line up, so here I have that extra plane of atoms in here, we're going to end up pulling some of the atoms apart. They have to stretch out a little bit. Some of them are going to compress together. We're going to get some shear off to the side here. And we're going to get this anyways if these atoms aren't all identical. So if one of these atoms is a little bit bigger or a little bit smaller, or if we put an interstitial atom in here, it's going to cause some stresses and strains in there. Because those are in there, they're going to want to somehow relax if they can. And one way for that to happen is the defects, these point defects, are going to migrate together with the line defects or dislocations. And so these dislocations and these line defects end up coming together. And that actually reduces the internal energy. And now because these line defects and point defects are together and they're kind of happy, they're at a lower energy state together, it's going to be harder to overcome that and get that dislocation to move. That's normally how we get plastic deformation, is we can move those defects, we can slide planes, we get that slip. And we don't get that if we can kind of pin that dislocation in place, and we can do that by adding substitution or interstitial defects. We can do strain hardening, often called work hardening. We can get a ductile material, we can plastically deform it. We do this when we cold work materials. We'll talk about what cold working is here in just a second. And again, what this does, it deals with dislocations. As we work a material, we allow these dislocations to move, and they're going to migrate and move throughout grains. It can be hard for them to move over grain boundaries, and so they tend to pile up. And as they get closer and closer together, I get these dislocation strain field interactions. As they get close together, these stresses actually begin to repel each other, and so it's harder for these dislocations to continue to move, because as they get close, they don't want to get any closer, and so they just kind of, again, we can pin those dislocations in place. And again, that hardens the material because we can't deform it as easily because those dislocations aren't moving. We're not getting that slip. We've talked previously about some thermal processing. We did that in our thermal video. we talk about annealing, normalization, quenching, and tempering. And so we can always go back and look at some of these things. We have some information on that here. But there's other thermal processes as well. We have precipitation hardening. That's also called aging. And what we can do is we can induce small, uniformly dispersed particles of some other phase within our material, which is of some other phase. That is maybe difficult to picture, but I did throw the word phase in there, and so we could think of this maybe as in terms of what do phase diagrams do. And so if we look at this material here, let's say that we're right here at this 90% B concentration, and room temperature is somewhere kind of low down here. So we're in this alpha plus beta phase. What I could do is I could heat up this material and we could keep it elevated until everything has become beta phase, and then I could quench it. I could freeze everything into the beta phase. Now, there's not going to be thermal energy for the alpha phase to come back, even though we're going to come back down to this lower temperature. We're going to be back down at this room temperature down here, but I didn't give it enough time for the alpha phase to start to come out of my material. And so I froze that beta phase in there. What I can do is maybe I can heat it up a little bit. I can add some thermal energy, not enough to go all the way into the beta phase, but I can add a little bit of thermal energy to start getting some of this alpha phase to come out. And if I do this just a little bit, then I'm just going to get a little bit of alpha phase. And what's going to happen is I'm going to get these small particles that are alpha that are going to be mixed in with a mostly beta structure, beta phase. And the reason we also call this aging is because this happens over time. I quench something and I freeze it, but there's always thermal energies around. And so over time, alpha is going to come out, but it comes out pretty slowly. I can accelerate the aging process by just adding some thermal energy. We can talk about recovery. Recovery is just when we release some of those internal strains. When I work some of these materials, when we work them, there's going to be a lot of these strains inside them, such as with strain hardening. And what we can do is we can somehow try to relax that. We can do that tempering. We can heat it up a little bit, not enough to recrystallize, but just to take out some of the strains and stresses in a material if we've worked it. There's recrystallization. I can raise it up to a temperature called the recrystallization temperature. And that's different for all materials. It depends on the material that we're looking at. And once I get to that temperature or a little bit above it, what I can do is I can form new grains. And these new grains are going to be mostly strain-free and equiaxed. And they're going to be small. They're going to be new grains. If we go back to, I believe it's this thermal, we have this picture here. So if I have this material all the way to the left here, I have this material, maybe we worked it a little bit. There's some dislocations in here. There's some stresses. Maybe there's some defects and whatnot in here. And I heat it and I get it up to that recrystallization temperature. Every place that there were some defects and some dislocations, nucleation sites, where there's a significant amount of stresses and strains inside the material, what's going to happen is it's going to want to recrystallize it. So I get a lot of little grains beginning to grow because every spot where everything wasn't perfect is going to want to straighten back up. And so it starts straightening back up in all these little spots. If I hold it at that recrystallization temperature for a while, I get grain growth. So I hold it at the recrystallization temperature or above it. And over time, what's going to happen is these small grains are going to start combining. And I get larger and larger and larger grains. And these grains are stress-free, they're equiaxed, they're about the same shape and the same radius, no matter how you kind of measure them. You're not going to get those textured grains. You're not going to get massive spots of stresses and strains within a material. The dislocations aren't going to be piled up anywhere. It's a way to relax and grow the grains. And there's different reasons for that, and depending on what we're looking for, we are often going to do a combination of all of these different types of things. Let's talk about some fabrication techniques, and I just listed out, we're going to talk about 6 different types here very, very quickly. The first one is casting. Casting is when we take molten metal and we want to form it. So one way we can do this is we can do it with an ingot. What I can do is I can just take a bunch of molten material and I can just dump it into a large place and let it solidify. Again, going back to this thermal picture, we talked about what happens. So I have this large mold here. I dump the molten material in there. We get all these little nucleation sites where it starts freezing immediately when it hits the side of the mold. We kind of get these columns, a little bit larger, textured grains with the equiaxed grains in the middle. But what we end up here is we have an ingot. These can be very, very large, but they normally, have this weird grain structure throughout them. At that point, a lot of times you're going to want to either remelt them down. It might just be a way to store it in an ingot, or you're going to start working it, something along those lines. A lot of times we're going to want to shape it. And instead of just working it to shape it, we can just cast it when it's molten, and we can end up with a shape where we don't have to do as much work at the end. And I have a few types here. We have sand mold or sand casting. What I do is I make 2 molds and I put an impression on both of them. I can fold those together and I can inject it with molten material. I can open it up once it's solidified, and the sand just kind of, goes away. I can break the sand away, and I have this thing that's kind of shaped like whatever the indentations were. I can do die casting. We get a metal mold, and high pressure, high velocity flow, we squirt the molten metal into it and we let it solidify. We have investment casting or lost wax. I can make something out of wax. I can dip it into some type of slurry, something like plaster of Paris. I can pull it out. I can let the plaster harden, and then I can heat up that mold, the plaster of Paris with the wax inside of it, and I can let the wax drip out. And now I have a mold, and I can pour metal into it, break away the plaster, and I have whatever I'm trying to cast. Lost foam is very similar to that. It's a combination of investment and sand casting. You can make a foam pattern. So you get something like styrofoam, and you can cut it and you can glue it together, and you can do all this stuff to make whatever you want. And then you bury it in sand. You just pour the hot metal over the top of it, and that foam vaporizes, and you end up being able to knock that sand away, and you get the metal in the place of where the foam was. And you can have continuous casting. Basically, you just pour the metal out, the liquid metal, and it starts solidifying, and maybe you put it on some conveyor belt or some rollers or something, and so the solid piece keeps moving. But it's all connected as you continuously pour it. And so you can end up maybe with these long sheets, and you just kind of keep pouring it. And as you kind of pull that material away that you previously poured, that will start solidifying as it gets pulled away. And you just keep pouring it, and you end up with these long pieces. So that's casting. What we could do is we could also form the material. We could work the material. This is what we call wrought. So when you have a wrought material like wrought iron, it is worked. It means that it's been forged or rolled or something. So I'm going to try to draw some pictures here. All right, so I could have, let's say, an anvil or something here, and I put my material on it. And then what I'm going to do is I'm just going to apply a force on the top. I'm going to squish it. And that's really all forging is. A lot of times we use machines to do this anymore. A lot of times, blacksmiths and whatnot would just use hammers. But what I can do is I can put it through 2 plates, and I can just smash it together. And what I do is we would end up having these forces. just forcing these two things together. Think of it as a hammer just hitting it, and you're smashing it, and you're smashing it, and smashing it. I mean, this can be done cold or hot. We have cold work and we have hot work. And in a second, with rolling, I'm gonna show you the difference between them. But remember, if you cold work a material, it's gonna harden it. It's called work hardening. And again, we're working the material here. There's one other way of forging. This would be considered an open forge. What I could do is I could do a closed forge. I could have something that has some type of shape and maybe some type of shape on the top. And then I just put my material inside of it. And then I just, again, start smashing these two things together. You know, they just start clamping down on top of each other, pounding like a hammer together. And these forces will eventually smash it into the shape of whatever shape we happen to have here. If it's not flat, then it's going to take the shape of whatever we're smashing it against. All right, so rolling, and I said that I was going to show you the difference between hot working and cold working here. So first, let's talk about cold working. So rolling is when I get rollers, and these rollers are going to rotate, and this is where the force comes in. Anytime I'm working the material, there has to be a force somewhere. So forces here, these also are pinned in here. So if I try to force something through here, these rollers can't move up or down. I'm gonna put my material in here on one side. And this material might have, you know, just a simple grain microstructure. But as it squeezes between here, I actually am gonna change to blue because I'm gonna show that this is cold working. So what we have here is it's going to smash it and it's going to change the shape. But what happens to the microstructure when we do this? These grains, these larger grains, are going to flatten out. We end up with a textured material here. And within those grains, our dislocations move. We're going to have lots of slip happening. And so we end up with grains that have really been stretched out. They've been worked, and there's a lot of stresses inside of there because of that. I am going to draw this one more time, but I'm going to show what happens if we hot work the material. So here is the rollers. They're spinning, adding a force. I'm going to use red for a hot material. And so let's say that I have this grain boundary here like this. As I roll it, again, it's going to start putting these stresses in here. But because it's hot, there's enough thermal energy for them, instead of just getting stretched out and having to slip, every time that we kind of put this force in here, it's just going to recrystallize. It's going to say, you know what, we can't hang out with that grain up there anymore. I know we used to be a part of it, but we're getting so stretched out. Luckily, we have enough thermal energy that we can just become our own grain. And so what you end up with when you hot work a material is a bunch of little grains. If I were to keep this up, so let's say that I'm going to be doing this, I'm going to hold it hot for some time, then these will start growing again. So when you hot work a material, you're going to get small grains without much internal stresses in them. When you cold work material, you're going to get a textured grain structure, and you're going to have a lot of internal stresses. Real quick, extrusion. All these actually have compressive forces so far, right? I compress when I forge. There's compression happening when I roll. Extrusion's no different. What we're going to do is we're going to have some shape here. I'm going to put some material in here, and I'm going to push it through. It's going to be compressive. I'm going to push it that way. That's my force. And I have this little opening here, and the material is going to come out of there. It's going to come out smaller, of course, because it has a smaller opening. Now, drawing is slightly different than the rest. There's still a force because we're working the material, but instead of a compression force, we have a tensile force. So here's my opening. We'll go ahead and put the material in right here. And as it comes out this other side smaller, the reason it does it is because we're actually pulling on it. So in this glass case is when we're drawing a material, the force is in the front of it. The rest of them, the force is behind. We're pushing it through, we're smashing it, we're doing those things. In this case, we're actually pulling it out. All right, those are mainly for metals. Not completely, but they're often for metals. Molding is another thing that you can do, and that's usually what we refer to for plastic. It's very much like die casting, but with plastic. I get a mold, and I inject softened plastic into the mold at a high pressure. And it cools, and we open up the mold, and I get my phone case, or I get, you know, the toy that I can snap together after I put the electronics inside of it. We can join things together. That's pretty simple, at least on the surface. We can weld it, we can solder it, we can fasten it. I want to put two things together. But even in here, there's a lot of different types of welding. What type of fasteners do we want to use? Or, you know, what type of solder, or is this good for solder or whatnot? So it's still very, very in-depth. We can machine something. Machining is a subtractive process. If I cast something, normally it's not going to have a nice smooth surface. It might not, depending on the type that I use. Let's say I use sand casting. It's not going to have a nice smooth surface, and so I'm going to have to go and I'm going to have to smooth that surface out. I can do that by turning, I can drill, I can machine it somehow. But what I'm doing is I'm taking off small layers of a larger thing. I can do the opposite. I can add things onto it. Maybe the most common one that people think about is 3D printing. I add lots of little pieces of plastic and I end up with a larger structure. Some other ones would be chemical vapor deposition. That's a chemical reaction. I can put something in a chamber, cause a chemical reaction to happen, and on the surface of a material, we use the term grow. Sometimes we use that term. We can grow something on there. We can have this surface, we can have molecules attached to the surface, or I can grow nanotubes or something like that. Electroforming, that's like electroplating. So if I want to put a thin film of gold on something, I can go ahead and do that. So additive processes are a lot of times, we're just adding something on the outside of a material. And lastly, there's laser sintering, and laser sintering is pretty cool. You have this little chamber with a bunch of powder in it, and you have this laser, and this laser kind of shoots at this powder, and wherever it's supposed to, it solidifies the powder. And it's a lot like 3D printing. The laser goes through and it solidifies different portions of the powder, and then you pull this thing out later and you shake off all the excess powder and you have this solid material. There's lots and lots of ways to process this. Again, it's just a very, very simple overview. The things that I find very interesting about this are the things that tie back into what we've talked about already, how the thermal works, the microstructure, pulling it back to composition and microstructure, looking at grain boundaries and the energies and all of that within there.